Hello, today we're going to do a very hard integral from the MIT Integration Bee. Well, it's very hard if you don't know where to get started. Now, it is part of like a family of integrals that relate to the Basel problem, which actually is the sum. So it's the sum from n equals 1 up to infinity of 1 over n squared. Now, this is a very famous problem. We're not going to prove it because it's pretty difficult. But we're going to use this as a fact. So if you know the technique for this integral, it's not too difficult. Definitely give it a try. If you can do it, really well done for that. Now, how are we going to solve it? I presume there are many solves for this one, but the one I found the most straightforward was this one. So we're going to start off by reciting this integral from 0 up to infinity, and then we're going to multiply by e to the power of minus x. So both the numerator and the denominator. So we're going to get x, we're just going to put that in front, and then times e to the power of minus x times e to the power of minus x plus 1 over e to the power of minus x times e to the x minus 1 dx. So we've now got this new integral, which is even more complicated, but we're going to distribute some terms here, and then we'll get a clear result. So we're going to get the integral from 0 to minus infinity of x times e to the power of minus 2x plus e to the power of minus x, and then we're going to get e to the power of 0 minus e to the power of minus x dx. So now we've got this next integral. Now notice that we can write e to the power of 0 as 1, and we've got this new integral. So why have we done that? We're actually going to use some series representations. So let me get rid of this Basel problem here, and we're going to use, first of all, the series for 1 over 1 minus x, which is equal to the sum of n equals 0 up to infinity of x to the power of n. So let me write out some terms here to notice why that is true, maybe. So actually, if you do some long division, you can get this answer. This is also a geometric series, but that also tells us that x, or the absolute value for x, has to be smaller than 1. So if you don't know this result, don't worry. It's not necessary to know why this is true. It's also just a Taylor series, so if you're not familiar with that, don't worry. It's a pretty nice result. So we're going to use this. But we're going to plug in something else for x. Mainly, we're going to plug in e to the power of minus x. So we're going to get 1 minus e to the power of minus x, which is going to give us the sum from n equals 0 up to infinity of e to the power of minus x to the power of n. So notice what we've done here is we've just plugged in this new function for x. So let me write out some terms. Now that we've done that, we can actually notice why we rewrote this integral a little bit, because we could have done some similar stuff with the first integral, but now we can see why the absolute value of e to the power of minus x is easier to be equal to be less than 1. It's not completely convergent on this interval of our integral here, so at 0 it's not actually convergent, but we're going to ignore that. It works fine. Well, it's just one point in a complete integral, so that doesn't actually matter too much. Now we're going to rewrite this a little bit still. We're going to get e to the power of minus x times n. So that's just taking that power and multiplying it. Now, the next step we're going to do is we're going to use this in our integral. So maybe let's get rid of all of this. And we're going to rewrite our integral. So we're going to get the integral from 0 to infinity of x times e to the power of minus 2x plus e to the power of minus x. And then we're going to get our result that we just got, which is going to be the sum from n equals 0 up to infinity of e to the power of minus x times n, and then also in the integral dx. So now we're going to apply a trick, which doesn't always work, but it does in this case. And we should actually verify that, but this video will be long enough without doing that, so trust me on this one. We're going to switch the integration sign with the summation sign. So we're going to get the sum from n equals 0 up to infinity of the integral from 0 up to infinity of x times e to the power of minus 2x plus e to the power of minus x times e to the power of minus x times n dx. So in the next step, we're going to split this integral up into two pieces just to make it more clear what we're going to do. So we're going to actually split it up into two sums of integrals. So what that's going to give us is going to be the sum from n equals 0 to infinity of the integral from 0 to infinity of x times e to the power of minus 2x times e to the power of minus x times n dx plus the sum from n equals 0 up to infinity of the integral from 0 up to infinity of x times e to the power of minus x times e to the power of x minus x times n dx. So now we've got these two integrals. The reason I've done that will become clear, otherwise we're going to have to do a lot more calculation. But before we do any of that, we can actually combine these powers of e. So this part we can write as e to the power of minus x times n plus 2. So that's just power rules, and in this case we can write e to the power of minus x times n plus 1. So now what we're going to do is we're going to change our summation a little bit. So notice that if n equals 0 on this first integral, we're going to get e to the power of minus x times 2. We're just going to change that slightly so that we can work with this easier. So we're going to change n from n to n minus 2, which means in our sum that n has to start from n equals 2, and we can substitute that into the exponent here, which is going to give us n, like so. And we're going to do basically the same thing for the second integral here. We're just going to substitute in n minus 1. So that's going to give us n equals 1 here, and the same exponent there. So notice what we've done now is we've got twice the same integral, and we're just going to compute one of these, and then we're going to do these sums. Notice that these sums are a little bit different, so we can't just assume anything too quickly here, but let's do these integrals using integration by parts. So I'm going to use the DI method for integration by parts, which is a really quick way to do integration by parts continuously, repeated several times. If you don't know how it works, there are several people who have great videos on it. There are also websites on it. I'm going to explain it as well along the way. But basically, we've got this sign column, which is going to give us the sign that we have to multiply with. So we've got 1, minus 1, or 1. We've got this column of differentiating, so that's going to be our x column. Now we differentiate that, that's going to be 1 and 0 if we differentiate again. And then we've got this integral column where we need to integrate our function. So notice that the multiplying this first row is going to give us the function in our integral. Now we're going to integrate these functions as well. So that is just a basic function which is going to give us minus 1 over n times e to the power of minus x times n. And then again is going to give us n over 1 over n squared times e to the power of minus x times n. And this is going to be our final integration. So how do we read this table? We're actually reading it as, so we always multiply by the first number, And then we read this sideways if we just multiply, so like this, diagonally, or horizontally if we take an integral. So to get a clearer explanation of what's going on here, definitely look it up, but you'll be able to follow along just from the context here as well. So what is this integral from 0 up to infinity of x times e to the power of minus x times n dx equal to? We're going to get, so as I said, diagonally, we don't have to integrate or anything. We're going to get minus x over n times e to the power of minus x times n, evaluated from x equals 0 up to infinity, like so. We're going to evaluate that in a moment, and then again diagonally, but now we again have to multiply by minus 1, so we're going to get minus, and then 1 over n squared times e to the power of minus x times n, evaluated from 0 to infinity. And then the last integral here, or the last step here, is actually just this horizontal multiplication and taking the integral. But since we multiply by 0, that it'll just falls apart, and we don't need to do anything with those things. Now, for this first bit, we're going to have to notice that when x equals 0, we just multiply by 0, and e to the power of 0 is just 1, so we get 0. And when we take a limit as x goes to infinity, well, the exponential function is going to be way smaller than the x function is getting bigger. So we're going to go to 0 again. So this entire part can just be erased. And then the second part here, that's a little different though. So we need to take the limit as x goes to infinity. Well, that's just going to be 0 because we're going to get an incredibly small number, infinitely small, so we're going to get 0. But when x equals 0, we're going to get something different here. So let's just plug that in. Now notice that the 0 is the lower bound, so we need to use another minus sign. So we're going to get minus minus, or just plus, and then 1 over n squared times e to the power of minus 0 times n, which gives us 1 over n squared. So that's nice. We now have that this integral equals 1 over n squared. So when we fill that in into this above equation here, we're going to get the sum from n equals 2 up to infinity of 1 over n squared plus the sum from n equals 1 up to infinity of 1 over n squared. So that is extremely nice. Now the only thing we need to do here is we need to consider that the first sum goes from n equals 2 and the second one from n equals 1. Now what we can do here is we can actually just add in the first term in this first sum. So how are we going to do that? Let's just erase a bunch of this stuff. We're going to do that just by, first of all, we add in this first term, n squared, and then we rewrite our second sum from n equals 1 to n squared, to infinity of n squared. And then, of course, we added in this first term by changing n equals 2 to n equals 1, but then we also need to subtract that first term. Now what is that going to be? We're going to have to do minus 1. So check if that makes sense to you, and now we can just compute this last part. So we're going to get twice the sum from n equals 1 of n over n squared, of 1 over n squared minus 1, which is going to give us 2 times the Basel problem, pi squared over 6 minus 1, which is going to give us pi squared over 3 minus 1. And that is our final answer. So as we rewrite our integral, we're going to get the integral from 0 to infinity of x to times e to the power of minus x plus 1 all over e to x minus 1 dx is equal to pi squared over 3 minus 1. So I hope you found this integral interesting. It definitely uses some interesting techniques. I think it was brilliant using the Basel problem as well. Of course, it's not as neat because we just use this result without proving it. But yeah, it's too much work to do the Basel problem as well in this video. Now, thank you so much for watching. I love this integral. If there was a way simpler way of solving this, definitely let me know. I'm pretty interested to see if there's some elegant trick I missed here. I thought that this was actually pretty straightforward. So thank you so much for watching and getting through this difficult integral with me. Let me know if you've any tips whatsoever. Till next time.